Hello, and welcome to another lecture in this course. Today we're going to look at the Cauchy-Riemann equations, which is subsection 212 in the book. That's basically telling us the relationship between the real and the complex derivative. So, suppose that we're in an open set in C, and we're going to think of C as R2, as we often do. As a set, they're the same, right? So as a real function, so really thinking of a function from U in R2 into R2, that is differentiable in the real sense, in the standard normal calculus sense, if there exists a real linear operator, a 2 by 2 real matrix, df, that's how we're going to call it. We're going to put the at z naught, right? But this is just that's just our notation for this 2 by 2 matrix, such that this limit exists and is 0, right? So basically, we take the f, we look at it a little bit away from an h, h step away from z naught. We subtract f of z naught, and we say, how is this different from just applying this real linear operator? And we say that this error had better go to 0 faster than h. And again, this h varies in C or in R2, however you want to think of it. It's the same set, right? So it's not this is not a real number. This is a complex number. All right. Now, from calculus, from just basic vector calculus, you find that, well, if this matrix exists, it's actually equal to these partial derivatives, where I've done this for the standard use of letters in complex analysis. You set the real part to U and the imaginary part to V, right? So those are the two components of your function, and so we have this 2 by 2 matrix, right? You notice that the first row corresponds to the first component, second row corresponds to the second component, right? First column corresponds to the first variable x, right? The real part of z, and the second corresponds to the imaginary part of z, right? All right. So, question is, when does this matrix correspond to multiplication by a complex number, which is what that's what we want. We'll see in a little bit. That's what that will mean, that it's complex differentiable. So when does this real matrix, real 2 by 2 matrix, correspond to a multiplication? When is it a multiplication by a complex number, right? We know that not every real linear operator is a multiplication by a real number, by a complex number, sorry. Well, we've looked at this before, and we noted that it's precisely when it's of this form, right? It's this a minus b, b, a, right? And then it corresponds to the multiplication by a plus ib, right? And that's an if and only if, right? So that means, in terms of our real derivative, it means that, well, I have to have that a, right? This term has to be equal to this term. I get this equation, right? Then I have to have that this minus b has to be, well, minus b, right? So I get that this has to be minus this, right? I get this second equation, right? These are going to be what we're going to call the Cauchy-Riemann equations. All right. Now, if we have these, right, if the function is real differentiable, so it is this matrix, and we get these equations, then this matrix corresponds to multiplication by number, which is the a plus ib, which you can actually read off from these partial derivatives, right? That's sometimes useful as well. I mean, it doesn't mean that, I just take some random function, I compute these guys, and I say, well, that's the complex derivative. Well, no, I mean, the complex derivative would have to first exist, right? So you have to have this thing, right? All right, so why is it the complex derivative, right? Well, so suppose that it is multiplication by a complex number, right? It's some c times h, right? So we'll plug it into the definition of the real derivative, right? I mean, this is what it means for that that real linear operator, which is now c times h, to be the derivative, the real derivative of f. So we just do a little bit of algebra, right? We pull the absolute values out, and then we can cancel out the h on the c, and we get that this guy goes to 0. Aha! That means that this limit exists, right? Well, that's precisely what we said in the definition. That's the complex derivative, right? And c is that derivative, right? So we have that f prime at z0 exists and is equal to c. So we proved that if f is real differentiable, so if there exists this matrix, and we satisfy these two equations, right? Because everything is at a single point right now, then f is complex differentiable at that point, and the derivative is, of course, that that number that represented by the 2x2 matrix. Now, conversely, right? If we are complex differentiable, if f is complex differentiable at z0, sorry, right? So that means if f prime exists, well, let's look at this slide again, right? If this exists, right, then that's equivalent to this thing being 0, which is equivalent to this thing being 0, which means precisely that this thing, which is the complex derivative, is the real derivative, right? So that means that the real derivative exists, right? So what we have is that if the function is complex differentiable, then it's definitely real differentiable, right? And furthermore, of course, we get that that these equations must be satisfied then, right? Because it's not just real differential, it's also complex differential. So the derivative corresponds to multiplication by a complex number. All right. So what did we prove? We proved that if we have a function defined on an open set U, then f is complex differentiable at some point z0, if and only if f is real differentiable at that point, and you satisfy these Cauchy-Riemann equations at that point, right? So if you are real differentiable, satisfy the Cauchy-Riemann equations, then you're complex differentiable, and vice versa, right? So it gives us a way of checking that that something is complex differential in terms of the real derivative, right? And in this case, we can actually compute it. Once it is complex differentiable, then once this thing exists, right? Then that's we can compute it using one of these two expressions. Now, checking that something is real differentiable is not always so easy. There is a there is a useful way of checking, which is not really an if and only if. It's easy to compute by basic calculus. It's easy to compute the partial derivatives, right? But just because the partial derivatives exist at every point, that doesn't mean that the function is real differentiable. That doesn't mean that this matrix exists. However, if those partial derivatives are continuous, then it is sort of a basic calculus theorem that then it is differentiable, real differentiable if matrix exists, right? So we can use that, right? And so we have this corollary. If you have a function, right, and all the partial derivatives exist and are continuous, right, which will imply that the function is actually real differentiable, right? Usually it's called continuously differentiable, right? Then the Cauchy-Riemann equations, and by this I mean at every point, right? So this is satisfied in U, right? Is then the Cauchy-Riemann equations is equivalent to F being holomorphic, right? Complex differentiable in at all points, right? Just it means this, right? Which seems a little like a different thing, right? That we're doing, right? This limit exists whenever we satisfy these equations, right? Now you have to check the continuity for this to work. So these equations, as we said, right, these guys are called the Cauchy-Riemann equations, right? And basically, complex analysis is the study of their solution, right? Or various solutions. Now, you want to be a little careful. I mean, you sort of have to try a little bit to find a counterexample, but it's not true that just if the partial derivatives exist and happen to satisfy the Cauchy-Riemann equations, that doesn't mean the function is holomorphic. It doesn't really mean much at all. It doesn't even mean that the function is continuous, right? So only getting the Cauchy-Riemann equations is not enough. I mean, you have to have something. For example, that the partial derivatives are continuous. And we'll see an example of this a bit later on. So you can you can use the Cauchy-Riemann equations, but you have to check something, either real differentiability, which is a little hard to check, or the continuity. And that's actually quite simple. So for example, there's a very simple exercise, right? You take e to the z and you check that it's holomorphic, right? Using that corollary, right? And from that you get that sine and cosine, the complex sine and cosine, which are defined just in terms of e to the z, are holomorphic, right? Right, so the hint is to write it in terms of x and y, right? Take the real and imaginary part, show that the partial derivatives exist and are continuous, and satisfy the Cauchy-Riemann equations. And that gives you that e to the z is holomorphic, that the complex derivative exists, right? So now we have our first sort of, maybe, and you can even compute the derivative, right? The derivative is just going to be itself, right? E to the z. All right. So next time, what we're going to do is we're going to look at some basic calculus with holomorphic function, with the complex derivative. Just basically whatever follows either from same arguments in one real variable or what follows from knowing the real derivative, and so on, right? So just a very simple calculus. So that's what we're going to do next time. So see you next time.